Hello, everybody. So what this video is going to be is it's going to be kind of a supplement to section 3.1 and maybe a little bit of 3.2 in your book. Um, we'll say it's a bonus lecture. So there's just a couple of things that ended up in the homework because I didn't write the homework. And maybe it's a little bit tricky. It's not clear what to do, and I don't want you to have to, just Google it. So hopefully this will alleviate some of your concerns with this stuff. So in these sections, kind of let's start with what I expect you to know. So in section 3.1, we are talking about curves. Talk about curves. And the first curve that you deal with is actually before section 3.1, and that is straight lines, right? So you've seen parametric curves before this, parametric equations of a line, right? And those equations look like this. So like x of t could be, it's like a constant times t plus like some initial x value, a different constant times t plus some initial y value, and a third constant times t for some plus some initial z value, right? And we know how this works, right? Like if you wanted to try to plot that, well, I guess we could also say that, the direction vector, I don't really need to summarize this now because we should already know it, but like the direction vector for this is like, we'll say D is ABC, and the line goes through the point x naught, y naught, z naught, right? Maybe the notation used is not always exactly this notation, but we should already know this, okay? And this is we call these parametric equations because there's a parameter, one parameter. Parametric equations because each of the variables we care about, x, y, and z, are functions of a parameter. T. Now, if there were two parameters, we would be dealing with a surface and not a curve. Now, this curve doesn't really curve, right? Because it's a straight line, but in principle, it's the same. So any curve, well, not any curve, I should say, but in parametric, if you have parametric equations of a curve, it will look broadly similar to this. So if you have any set of equations like this, x of t equals, some function of t, y of t, some other function of t, and z of t, some other function of t, is going to be maybe with some range of t values, I'll say over, a less than or equal to t, less than or equal to b, those could be infinity, is a set of parametric equations for a curve. And so you're already supposed to know this. A curve. Okay. Now, if you think back to Calculus 2, something that some of you will have learned and some of you probably didn't was some basic parametric equations for things like circles. So you may have we have learned this parameterization from Calculus 2. What parameterization? This one. So let's say x of t equals cos t, and y of t is sine t. And if you make a table of values for this, which would look like this, so when we're trying to plot parametric equation, we need a range for the parameter, and then we need to keep track of our x and our y values. So for the t values, you pick whatever you want. I'm just going to pick 0, let's say pi over 4, pi over 2, and then I'll get lazy and do this. So I pick these t values, I plug them into these equations that I've written over here on the left, right? So like this first line here, so if I'm trying to do this first line, I would say, well, x of 0 is cos 0, which is 1. Y of 0 is sine 0, which is 0. So I have an x value of 1 and a y value of 0. And if I continue this process on, right, like I go x of what's pi over 4, well, that's cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So that's root 2 over 2. And of course, the y value there is also root 2 over 2. If I continue this process, what I'm going to get is that a 0 and 1, then I'm going to get a 1, 0, and then I'm going to get a 0 minus 1, and then I'm going to get a 1, 0, I think. Hold on. This should be a minus 1. And if you go and you plot these, what you're going to see, I put, let's say, 1 right there, and say root 2 over 2 is about there. And if I put 1 there, and then I put root 2 over 2 about there, what we get is that the first point, the one that's highlighted, is 1 comma 0, which is right there. The next one is root 2 over 2, which is about here. And then 0, 1, which is about there. The next one is negative 1, 0, which is over here. I didn't mark it. Then we have 0, negative 1, which is down here. And then finally, we're back to 1, 0, which is right here, where we started. And so what's going on here is that this curve being traced out, well, if I could draw it better, which I can't, like that, even got an arrow on there, right? That traces out a circle. And you're just kind of supposed to understand this, right? Going into all these problems, that this type of setup with one variable being cosine and one variable being sine is going to trace out a circle. If we extend this and we look at some more complicated problems, maybe with 3 variables now, we could have a set of equations like this, where we say x is going to be cosine t, y is going to be sine t, and then z, let's just make z to be like, let's say like 5t, something like that. Of course, you can go through and you can make a table of values the exact same way that we made a table of values for this previous one, but now you have to add on the z variable. And so when you do that, you're going to get like 0 times 0 is 0. And you're going to get like 5 pi over 4. We're just multiplying the t value by 5, right? Because that's what I used here. So t is pi over 4 multiplied by 5. So then we have like 5 pi over 2, 5 pi, 15 pi over 2, and 10 pi. And so actually, this is everything I wrote here is fine. I'm actually going to erase these because I realized I did this in the wrong way. I want t over 5. Actually, let's just do t over 4. Yeah, this is what I want. Sorry. The reason I want this is just because I want this to look a certain way. So sorry. So I'm just going through and putting in t over 4 in here. So dividing by 4. So yeah, so these are the z-values that we would get. And so what's going on here is if you take a set of 3D coordinates, right? You have x and you have y and you have z. Well, if you were looking down on it this way, right, you would see the x variable and the y variable, and you would see a set of axes like x, y, and it's going to be that same circle that we've already looked at, right? Like that's the circle that we've already plotted if you're looking at it from that direction. But what's happening is while it's tracing around circles, right? While it's tracing around this circle in the xy plane, the z value is just going up. So the z value is just going up to, that's pi over 2, which is like 1.5. So what's happening is you're getting this. As it's making circles, it's also moving vertically, right? And we've only plotted, this is only one full revolution. So this would be like from this point right here to this point right here. So actually on the, this section is only one full revolution. But if we keep going, then the x and the y values are going to keep making circles and the z is going to keep going up. Okay, and so that's not like super hard to understand. I think everybody kind of gets that. But you do need a good understanding of this before you get on to those more difficult problems. And that's why I was going over that again. So I'm going to switch to my computer real quick. So here we go. So we're looking at the homework. I can't see what I'm recording, so hopefully this is recording properly. So when you're looking at some of these problems in the homework, which, why doesn't it let me scroll? Okay, if I zoom in too much, it doesn't let me scroll. Then it's not that hard to see what some of these are. So like this second one here, can't really highlight it, but this second one here, where it's cosine t and sine, well, cosine t and sine, you know that what that's going to look like. So cosine t sine. Let me undo that. So if you were looking at, so this is like question 4 here. If you're trying to figure out what does r of t for cosine t sine, is that what it is? I think that's what it is. Let me check. Yeah, cosine t sine t. So if you have this and you're trying to figure out what it looks like, well, this time this is the x and this is the, no, that's the z, and this is the z. So it's in the xz plane, right? So xz plane, it's making those circles, right? Instead of the xy plane, it's the xz plane. And it's the y variable that's increasing. So when you're trying to match that up with a graph, right, this is the y and this is the x. So it's making, in the xz plane, which you have z here, you have x here. So like this is the xz plane. That's the one it's making circles in. So if you were looking at it from this way, I don't know why I did that with the highlighter. This is the one where it would be like making circles like this in the plane. But while it's happening, it's moving this way. So it still makes these spirals. But this time they are along the y-axis, right? So you're looking for a graph that does that. Okay, let me make this big. Let me do that. What happened? I didn't, it didn't do it. It just lost the thing. Oh, and it's back. I have no idea what's happening there, but we're okay now. So if we are looking at this, then you're looking for something that makes circles in the XZ plane. And so you can rotate this just by clicking it and dragging it. And this one, right, if you click it and turn it this way, you can see the Y is in the way, but you can see an X up here and you can see a Z here, right? And so this one looks a lot like we would expect. And of course, if you rotate it, it's still making those circles. So this is called a helix, and this is a helix, probably this one. Okay. Now, a lot of these are variations of the same thing, right? Like look at this, this one. This one, it's X and Y are sine and cosine. So on this one, you're looking for something like this, but not the X and the Z, you're looking for the X and the Y. So this is clearly different. This one looks like circles in the XY plane, and it's making that same kind of helix shape like we've seen. So this must be it. So what one was that? That was C. So you can pick C there. What's going on here? Looks like a tornado, right? Well, that's a different thing. How does that happen? Well, if I get rid of this, and we're back here, let's think about what happens if you have this kind of graph. So what I didn't do was this. So let's look at the previous example. Let's make a change here. What if I took this and I put a 2 right in front of that cosine? What would happen, right? If I put a 2 right in front of there, it still basically works the same. But what happens is the x value now goes up to 2 and minus 2, right? Because normally a sine and a cosine is stuck between, I put a 0 there, I don't know why. Normally, like a sine or a cosine is stuck between -1 and 1, right? But if you put like a 2 in front of it, it's going to be between -2 and 2. So what happens here is if I go out to 2, and this still only goes up to 1, then you're going to get this kind of shape, right? An ellipse. Still goes around that way. Point is you can adjust the size of this circle by changing the coefficient out front. And once you have that idea, you can say like, well, what if I were to take, let's take our base one, like the cosine t, sine t, t type thing. And what if I put a variable in front? What's that going to do? Well, what that means is like, that's basically like the radius, right? That's how big the circle is. So when t is small, this is making small circles. When t is big, you get big circles. So what happens with this kind of thing is it's trying to do what we talked about before, where it's trying to do this. But this is as the t values get big. So here t is big, and down at the bottom, t small. And so what happens in the picture is it starts out actually not just small, it starts out as 0. So it's making bigger and bigger circles as it goes up. So that's how you get that kind of tornado shape. And actually the sides here are going to be kind of straight because the speed that it's increasing vertically is also the speed that the radius is changing. So you kind of get this like conical shape here. So if I were to, wait, hold on. What happened? I don't know what I just did. Okay. So we get this conical shape, and then that's what this is, right? So so a cosine, a sine, and like a t cosine and t sine, that's how you get that kind of thing going on. Now, how fast it increases, well, that's going to be relative to these numbers out front, right? So looking at this, the only one I see that has a coefficient in front of the cosine and sine, a variable coefficient in front of the sine and cosine, is this last one. So even though this is a t squared and a t squared, this is still the only thing that could be doing this. So this must be D, right? And you see other things going on here as well. So like this one, you look at it, X and Y are making circles. So you look for cosine and sine as two of the variables. So that happens here. That happens on this first one. It also happens on this third one, right? Cosine, sine. And, well, which one is it? Well, let's think about it. We know that when you have cosine t, sine t, t, like this one, right? You get a shape like this. It makes circles, and one variable is just increasing. But this is increasing at a linear rate, which means that kind of everything is evenly spaced here. If you were to take this t and you change the variable so it increases at a different rate from the rate that it's rotating, then this could be stretched out or squished down. And so that is what's happening on E, right? Like down here, it's oscillating slowly and then quicker, right? That's what it looks like. But what's actually happening is it's making circles, and the speed that it's going up is changing. And that's what you're seeing here. Now, I wanted to talk through most of these. Now, this one right here, by the way, is a little bit harder to see, but I wanted to talk through most of these before I went through graphing them, because you can graph these pretty easily on a computer. What you would do is you want to go to Geogebra, geogebra.org, do Start Calculator, and then change graphing to 3D calculator. Just checking. Okay. So you can plot lines, curves, surfaces, all kinds of things on GeoGebra. And the commands that you use are just what you're trying to plot. So like if I'm trying to plot a point, I say point. And then I could put in like 3, 2, 3, 1, 2, right? It kind of, actually, I don't think you say point. I don't want to do that. I'm changing it. Sorry. 3, 1, 2. Okay. So you can do 8, like I should have said just something like this. So you can do a point pretty easily. Rotate this in space by dragging around in the window, click and drag. That's easy. If you want a vector, you can do that too. I can put in another point actually. Let me put another point. 2, 0. -2, why not? Right, there's a point. So now I've got 2 points in space. And if I want a vector, I just start typing vector. And then you can do, if I want it to go from A to B, I can do A, comma, B. If you just do vector A, it just makes a vector going to that point. B. So you can make vectors like that, and you can do cross products and all kinds of things on here, by the way. Like, for example, like if I do like V equals vector, let's say I just want a vector. Did I get one? Oh, I didn't spell vector. Vector. Right, so that's just another vector, right? So I've just got a couple of vectors. If I need the cross product, for example, or the dot product, I can say cross. And then those vectors have names, U and V. So I can get a vector that way and, that one. Anyway, that's not really what we're trying to do here. What I want to do here is I want to plot a curve. So the way you plot a curve is you just say curve. Okay, and then you put in your formulas. So if I'm trying to plot cos t, sine t, that's what I'm trying to plot. But you can't just type cos t sine t, and say that's x, y, and z. You need bounds for the variables. I'll do t over 4 actually, like that first one that I plotted. What you have to do after you put in the x, the y, and the z terms, you say what the parameter is. So the parameter is t. And then you say what is the minimum value for the parameter. I'll say 0. Then you say what is the maximum value of the parameter. I'll say 2 pi. So I've now plotted one revolution, right? So if I look at it on top, it's only one full revolution of the circle and, one loop of this helix. If I want to change it, I can just click back up here and I can change the 2 pi to like 8 pi, for example. And you might have to zoom in or zoom out to see more or less of the graph. But there you go. And so you can do this and you can easily see the changes it makes to change the variables, right? Like if I change this now to t squared, you can see what the result is. Now you have to you see that the cosine sine t squared, that's the same sort of thing that happens on E. It's a little bit misleading when you look at this graph that's supposed to be that, because this one's going up. It's just showing a lot of the graph that you're not seeing here, right? Like how far do you have to zoom out before you start to see what's going on there? Unfortunately, that's just the way it is. You can kind of, cheat a little bit if you need to make it bigger. Like I can put a 50 cosine and 50 sine, and we don't see it. But if I zoom out far enough, there we go. Right? So I just made the circles very large, and then it starts to look more like the picture that you have here in the homework. So they did that and they didn't tell you. I mean, they kind of just, the x, the y, and the z is just not quite what the scale is off. But you can plot these, right? So it's pretty easy to plot these. If you're trying to plot a surface, you can do the same thing. Surface. Like if I want to try to plot, let me just get rid of this actually. Hold on. If you're trying to plot the surface of, like, let's say, one of the, what they're called, like an elliptic paraboloid from the previous section, you say x will be x, y will be y, and z will be, well, what's the equation for an elliptic paraboloid? It was like x squared plus y squared, like, for example. And then you, again, just like before, you have to give bounds for the x, or for the parameters, which in this case are x and y. So you have to say x should go between, let's say -2 and +2. And then y should go between -2 and +2. And when I type all this, what happened? That did it wrong. X, Y, Z. Oh, yeah, you don't say Z equals. You just say what Z is equal. Okay. Oops. I need to reset this graph somehow. Figure out how to do that. Okay. Not full screen. So there you go. So you can do a surface this way. And part of the reason I'm doing this is because this kind of thing where I put in x, y, x, y, x, y is because this is very similar to how I'm going to plot or how I'm going to solve some of the trickier problems in this section here. Okay, so let's look at here just to go to the bottom. I'm going to get a problem off of this list here. Yeah, let's look at question 8. So people have asked me how to do question 8 and 7 and 9 as well, but I want to specifically talk about it. So it says find the vector equation. So we need parametric equations. I don't know if they use the word parametric equations there, that represent z equals 3x squared plus y squared. Probably you'll have something different. And x, this is a surface. Well, these are both surfaces, so I just won't bother writing it. X equals e to the y. And then they say this little no is important. Write the equation. So one function is just t. Okay. Now, having written that down, I realize as soon as I just did it that that's not quite what I want to do. So we're going to come back to this and solve it in a minute. Looking for my iPad. There it is. So we'll come back and we'll do this in a minute. It's actually very straightforward. So the general strategy for these is as follows. So to come up with equations with parametric equations of a surface. This section is not surfaces. This is curves. But to come up with parametric equations for a surface, and I'm going to make up a surface here, for example, let's just say z equals, let's say 2x squared minus y squared, right? Now that's a surface. That's like, what do they call that? Like a hyperbolic paraboloid or something. So, I mean, I don't care about that. We'll plot it in a second just to look at it. But how would you do this, right? Because this is not parametric equations. Parametric equations is when we have one equation for x, one equation for y, and one equation for z. And initially, you're not going to know how to do this. But what you have is, if it's solved for a single variable like it is here, what you do is you just say, well, my first variable, my first parameter, just use x and y as parameters. That's all you have to do. And then the x can just be x and the y can just be y. And then the z is 2x squared minus y squared. And that's it. That's your parametric equations. So you actually didn't really do anything. You just said x is x, y is y, and z is what they said z was supposed to be. And that works, right? That's what I was just kind of doing, or that is what I just did in Geogebra a minute ago to come up with those parametric equations. So you can do that. Or if you're trying to be fancy, maybe you do it this way. You change the name. So you say x is u, y is v, and z is 2. Well, it's supposed to be x squared minus y squared, but how about u squared minus v squared, since x is u and y is v? Right? Does that make sense? So this is kind of how you parameterize a surface. And the reason that's relevant is because in a question I think this is going to be like question 7. We're coming back to that 8 in a minute. I didn't realize what order would be best here. Was if I say this, if I say find equations of the intersection of surface about x squared plus y squared equals 9, and the other surface is going to be, how about a plane, let's say what do I want? I don't know. Let's say 2x plus 3y plus 4z equals 12. Okay. That looks hard, right? Because we got these two surfaces here. Oops, I don't want that color. We got these two surfaces here, and what's going on? But it's actually not that hard, okay? So what you've got going on is simply this. So your first thing, your first surface here is a cylinder, right? Remember, like x squared plus y squared is like r squared. So this is like a circle. This is really just like circle with radius 3. Radius 3. But then since z could be anything, it's actually going to be, right, like a cylinder because it's a circle that's been extended along the z-axis as far as you want. Okay, and then you've got this one, which is a plane. Well, this is a plane. I'm not going to try to draw this in exactly the right place because, well, I don't think my drawing, I don't think it'll be oriented in a way that is good. So I'm not going to really graph this plane. I'm just going to graph a plane. So this is just kind of a plane. Let's draw it like slanted out here, like this. And you can't really tell, but somewhere it's going to intersect. The plane and the cylinder are going to intersect. And like, let's say it's like this. So like, let's say, I don't know. That's not going to be the best drawing of that. But the point is that if a plane intersects a cylinder, it's going to like cut out a section like this, right? And then like everything above that, I can't actually erase that. I realize now, but like everything above this, right? Like this is all above the plane, right? Like cut that off, and you've got this kind of shape. So like the top is slanted where you cut it, basically. Does that make sense? So it's going to intersect in kind of this shape, kind of a tilted circle. So it's like an ellipse. And you might think like, oh, well, that's fine. I can see how that happens. But what do you do like about the intersection? How do we intersect surfaces? Right? That's going to be your question. How do we do that? Do we set things equal to each other? Right? A lot of people think that of that as their first idea. Do we set things equal to each other? No, you don't. Right? It won't work. Right? I mean, what you could do, and this is not going to do you any good, but like you could take this equation. What if you took this equation and you solved it for y, and then you plugged that in here? Right? That would work. That would get you an equation of the surface. So this would work, but it's not what you're supposed to do. What would work, but you don't do? 1. Solve the plane. I don't remember what it was. 2, 3, 4. 2x plus 3y plus 3z equals 12 for a variable. Let's say x. I'll say for x. Substitute into the other equation, x squared plus y squared equals 9. Okay. At that point, you'll have the equation of, what will you have? You'll have an equation just with y and z. And actually, I don't even know if this will work. It's just not what you want to do. So, I mean, forget it. I said what would work, but don't do it. I don't know how well this would work. Just don't do it. Here's what you do. Okay. That's going to be a better use of our time, what you actually do. So you've got these two surfaces, x squared plus y squared equals 9, and 2x plus 3y plus 3z equals 12. So what you do is this. Your first thing you want to do is parameterize the cylinder because that's easy. Right? Why is that easy? It's easy because we've already done it a bunch of times. That's just a circle, right? Like if you had like x squared plus y squared equals 1, that would give you the parameterization x equals cos t, y equals sine t, right? And if we want there to be a 9 here, 9, then we just need the radius to be 3. So you put a 3 here and you put a 3 here. Okay, so you parameterize that cylinder. Now, once you parameterize that cylinder, then you just are going to take the plane, 2x plus 3y plus 3z equals 12, solve it for z. Because remember, what we need is x, y, z. So we need to solve for z. So you solve it for z, so you'd get like 3z equals 12 minus 2x plus 3y. What happened? Oh, I put a 3 here instead of a 4. Oh, and I did that because I put a 3 here instead of a 4. It was 2, 3, 4, right? Yeah. Okay. So 4. So solve for z. So you just move everything to the other side and then divide by 4, which we don't need to be fancy about. Just divide by 4. And then at that point, you're essentially done because you already did 2/3 of it in the previous step. Now, parameterize, or rather just write your parameterization. So the thing is that x we already decided was 3 cosine t, y we already decided was 3 sine t, and then what's z? Well, z comes from the equation of the plane. So it was this right here. But we're just going to replace x and y with what they are. So this is going to be 12 minus 2x, but x is 3 cos t. And then plus, I don't know why I have a plus here, I just can't subtract. Minus 3y, and y is, we know, 3 sine t, and then just over 4. And then that's how you do that parameterization, right? And so the key here is just understanding that they're giving you these two things, and what you do is the one that has fewer variables in it, like this one, you try to use that to come up with your part of the parameterization, and then once you have 2 of the variables done, then you can go and do the other equation, which comes from the other surface, right? So this came from one of the surfaces, and then the z came from the other surface. So that makes the circles, and then that's on the plane. Okay, and that procedure worked for a lot of these problems, or a very similar procedure works for a lot of these problems. So like if we scroll up here to look at this one that I said we're going to skip, we say find parametric equations that represent these two things, and then notice the sneaky bit. They say one function is just t. They say that. So if you have x equals y equals z equals, you know that that's what you're trying to get. And they say one of them should just be t. What you do is you say, okay, well, in order to write z, you need x and y. In order to write x, you need y. So x needs y. So what if we just do this? So you just say, well, what if I just use y equals t? What happens if y is just t? Okay, if y is just t, then this right here is going to become x equals e to the t, right? I think so. That's it. So you just say x is e to the t. And now you've got x and y. So now that you've got x and y, you should be able to go to this equation and say, well, z is going to be 3x squared x is e to the t, so e to the t squared plus y squared, but y is t, and there you go. So 3e to the, that'll just be 2t, right? Plus t squared. And so that's a very similar process to what we talked about for the other problem, but I mean, there was a little bit of thinking involved, right? Not that much thinking, though. So these problems really look a lot harder than they are, okay? And you also have to kind of do this if you just wanted to plot this, right? Like, if you were trying to actually plot this curve, you would have had to do this work. Let's plot a couple of these. Like, let's plot this one, and then we'll plot let's plot the one that we just did, and then we'll come back. Let's plot this one. Parametric equations for this. So let me turn on the web browser. Let me find the web browser. Let me check the OBS. Yeah, okay. And so we'll try to plot that one. See how it goes. I'm looking at it. You can't. So let me go back to my web browser. So if we come here, Geogebra, 3D calculator, it like crashed or something? No, it's working. Okay. So like if I wanted to plot the cylinder, I could. I'm not going, or it's not a cylinder. We're trying to plot a curve. So curve. And how do curves work? We give the equations. So on the one that we just did, it was e to the t was x, t was y, 3e to the 2t was z, and we don't know, well, our parameter is t, and then what are our bounds for t? Well, we don't really know. Let's just go 0 and, I don't know, 5. Oops, need some commas here. T, comma, 0, comma, 5. And let's just plot it and see what it looks like. Okay, well, it's not that interesting, but we plotted it. Okay. It's not that interesting because the x and the z values are increasing very quickly, right? Compared to the y value. Exponentially fast here. So it's boring, but we did it. Let's do one of the other ones. Curve. So the one that I did for my plane. So like, let's do the OBS. Turn off the browser. So let's look at this one. Remember that this plane was not the actual right plane. I drew the wrong plane. But so we had x squared plus y squared equals 9. That was the surface. Actually, you know what? I'm going to plot that surface. So let me get rid of this. Delete. Delete. So let's do the surface first. So the surface was x should be x, y should be y. No, it was x equals cos t, y equals sine t, z just equals I don't know, anything, right? How do we do this? Oh, just z, I think. Okay, and then t can go from -1 to 1. Actually, the surface had a 3, 3, 3. So t can go from -3. This is killing me here. Hold on. 0 to pi. It's going in cosine and sine. All right. And then the z can go from, I don't know, -5 to 5. Right. So that's that's just the cylinder, right? And then the eventual curve that we got was this curve. And so the curve was, well, we actually used part of that same stuff, right? We had 3 cosine t was x, 3 sine t was y, but the z was the plane. We don't write z. The z was the plane. It was parentheses 12 minus 6 cos t minus 9 sine times t sine t, and then close that over 4. That's what we had. And then our first parameter, actually our only parameter was t, and well, I guess we just want to go between 0 and 2 pi for 1 full revolution. All right, and then there you go. And so I didn't plot this surface up high enough. Let's go up to like 10. Right, so you see that we did actually get that line. And if you wanted to, you could plot the plane, and the plane would just be slanted right through here, cutting through. And from on top, it just looks like the circle. So that's how you do those. It's how you plot them in 3D, and that's how you can work out the problems by hand. So are we looking at the problem now? I just realized that entire time I was doing that you guys were staring at my iPad, weren't you? Awesome. Well, poo. All right, we're going to start that over. That's what happens. So I don't know what happened actually. So we're going to do what I just said over. Let me load this again. Okay, there we go. It takes a minute to come back here. Delete, delete, delete. All right, so let's just do the super fast version of this. On this problem, okay, I see what happened last time. On this problem, right, we had the parameterization of this cylinder, right? X squared plus y squared equals 9, and these were the equations for it. And z was allowed to be anything. If we plot that, it looks like this. So I'm plotting the surface now, as soon as it lets me type. Okay, surface. So x was 3 cos t. The y was 3 sine t. The z could be anything, so I'll just put in z. And then our first parameter was t, and just 0 to 2 pi will get you 1 revolution around the circle. The other parameter was just z, which was allowed to be anything. And I'll just go like -5 to +10. So that's the cylinder. Okay, let's go back to OBS. That is the cylinder. Then we had the parameterization of that intersection, which used the same x and the same y, but then the z value was actually the equation of the plane, right? Just with what we had for x. What we had for x and y just plugged in for x and for y in the equation of the plane. So if you're trying to plot that in Geogebra, that's not that hard to do. Looks like this curve. So our parameterization for the curve was 3 cos t, same as above, 3 sine t, same as above, that's the y. But then our z this time is not just z, z is the equation of the plane, which is parentheses 12 minus 6 cos t minus 9 sine t over 4. That was the equation of the plane. And then we only have one parameter for a curve, and that parameter went from 0 and 2 pi. Okay, there we go. So sorry about that. But you can see that we've got the cylinder plotted, and also you can see that it's been cut at an angle through here. And that angle was from the plane, which I didn't plot, but you could plot the plane using the same method that we did up here, if you really wanted to. So yeah, so that's how this stuff works. If I go back to the homework maybe, then we can just verify that these are correct, right? So I think that was, so like if I'm doing this problem right here, how do you parameterize the intersection between, let me just double check that we're looking at the right thing here. Like how do you parameterize the intersection between a cylinder and a plane? What you're going to do is simply x, you parameterize the cylinder first, so like 3 cosine t. Okay. Oh, I didn't finish it. 3 sine t for the y. That takes care of the cylinder. And then if you plug those into the equation of the surface, z is supposed to be x plus 5y. Well, x is 3 cosine t from above, and then plus 5. 5 times 3 sine t will be 15 sine t, right? So that, I didn't even have to write anything. I'm able to just to do this by hand, and it's that easy. And if I plot this, it will look pretty much like this one, right? Although if you just plot the curve, you're just going to get the slanted curve here. You're not going to see the cylinder unless you plot the surface and the curve. All right, so we did this one as well. Same deal. The trick was realizing that if we just made y equal to t, then this first equation here, x equals e to the y, is now x equals e to the t. And then finally, z of t down here, well, it's just the equation given for z, but we plug in what we have for x and y. So what did we have? We had 3e to the, it was 2t, and then plus t squared when we plug these in. So these are pretty straightforward. Now, the last two on here, I do want to mention just briefly. These are really done more in, I think, section 3.2 than 3.1. But you're just going to do the limit the way you would do limit. So while I'm talking here, I'm just going to write down this first one. So we have the limit as t goes to 0 of negative 5e to the t sine 2t over t minus 4 squared. So let me get rid of that. So this is what we're trying to find the limit of. And just the key here is just that when you do the limit, you just do the limit piece by piece. So it's just going to be like a limit as t goes to 0 of negative 5e to the t, limit as t goes to 0 of sine 2t over t, and limit as t goes to 0 of t minus 4 squared. And so you just do those limits term by term, and you get what you get. So I think on all of these, you can just plug in the 0, right? So you plug in the 0 here for e to the 0. E to the 0 is 1. So you get negative 5. Plug a t equals 0 in here. Uh-oh, this actually has a 0 over 0. So you need to do something. So like off to the side, you can say like, how would you evaluate the limit as t goes to 0 of sine 2t over t, right? It's 0 over 0 indeterminate form. So it's indeterminate. So what do? I will do L'Hopital's rule, which normally is abbreviated L'H. And that tells you that you would be able to take the derivative of the top, d dt sine 2t, and d dt t, So we get the limit as t goes to 0 of the derivative of sine 2t is going to be 2 cos 2t, and the derivative of t is 1. And now you can take the limit as t goes to 0, and you're just going to get 2. So 2. And then finally, the last one, I think you can just plug in. So limit as t goes to 0 here, you can get 0 minus 4 is minus 4. Minus 4 squared is 16. So you don't actually need any new calculus here. You just need to know that when you do the limit of a vector valued function, you just do the limit of each of the three. So we got -5 to 16. Hopefully that's correct. Let's see. That's not what we want. That's what we want. Sorry, it just takes too many clicks to get back to where I am here. So enter a vector. So vector, we had -5, 2, 16. There's my vector. Easy peasy. And this is going to be exactly the same, but this is a limit as t goes to infinity. So you'd have to know what happens to these as t goes to infinity. And I guess it says we can make infinity symbols, which we're going to need. So like if you put an infinity into e to the negative t, you're going to get 0 because it's like 1 over e to the infinity. If you put into the second one, also e to the negative infinity is also 0. Then you have ln infinity. Well, ln infinity is infinity. So 0, 0. Why 0, 0? Because they said 2 O's make infinity. I mean, I could also, I hope this is going to be correct. If not, we'll get the infinity symbol. No, that's what it wanted. Okay. So you just take the limit term by term. And that's how you do these. Is there anything else I want to say here? I think the last thing I wanted to say here is just to pay attention, like if you're trying to solve these, like that's the answer key. No, it's not. But like when you're trying to solve these, you can graph them in GeoGebra. That's the easy way to do it. Graph the curve. Another way to do it is just to look carefully at like where the sines and the cosines are. So like on this, like for example, look at B. Because x is 3 sine t squared, I know that sine is between -1 and 1, and then you multiply by 3. So x has to be between -3 and 3. Also, z has to be -3 and 3. So if I rotate this to look at the x and the z, they need to be between -3 and 3. So like, for example, on this one, I've got like z on the side and x on the top. X is between, it looks like, I don't know, like -1.5 and +1.5. Z is between, I don't know, -7 and +7 maybe. Definitely not 3 and 3. So this, I mean, this could not be B. I mean, I know it's marked E anyway, but could not be B. This as well, right? Like look at the Y values, 0 to 40. Okay, no, not, or sorry, we're looking at X. X 0 to 50. That's not between -3 and 3. What about this one? X, it's bigger than 3, right? It's a little bit bigger than 3. It goes 0, 1, 2, 3, and a little. Z goes -6 to +6. Well, that's not -3, right? So that could not be B. This one's B, but you know, let's say we don't know that. If you look at X, here you see X go 1, 2, 3. -1, -2, -3. So this is X between -3 and 3, and then on the Z-axis, also between -3 and 3. So this is the only one that could be B just based on those threes. Okay? And that works for all of them, right? Like on C, the X value must be between negative and positive 6.75, and Y must be between negative and positive 4.25. So like those are different, but we can look at the x and the y. So where is y between, negative and positive 4.25, right? Like not here. This is like negative 2 to 2 or something. I don't know. Not here where this one's kind of crazy numbers. Here, what do we got? X between negative 3 and 3, y between 0 and 6. That's not right? That's not 4.25. Right? So which one could it be? Which one has the y between 4.25 and negative 4.25? Actually, I'm not finding it. Oh, not all equations will be used. Okay. That's why we're not finding it. But you see the point, right? So you can use that, like E has to be between positive and negative 1.5 for the X and the Y, right? And then you see that here, negative and positive 1.5, negative and positive 1.5, and then Z, positive and negative 7.25. So if you rotate this to look at the Z, oh, look, that one does look like it goes up like 0, 2, 4, 6, and more than 6. So it could be 7. More than 6 could be 7 down here, right? So like that's the easiest way to do problems like that, is to look at the bounds. All right, so I mean this video is going long, but I'm just going to take a glance at 3.2 real quick. I think this is just going to be calculus problems. So just if I see anything we have to do here. Derivatives. Derivatives of dot products. So second derivatives, easy. Tangent lines, easy enough. We do all these. The curves intersect at the origin. Find the acute angle of intersection. I think we've. I feel like you don't really need me to do that, but I'm going to do it anyway, just because. So I'm going to look at. So this is like 3.2.10. I'm writing it down. Hopefully, you're still looking at my web browser. So we have R1, t to the t squared for t to the fifth, R2, sine negative 2t, sine negative 5t, t, they intersect at the origin. Okay, find the angle of intersection, acute angle of intersection. Okay, so let me get rid of that. Here's what's going on. I'm not going to draw the exact curves because I'm lazy. I'm just going to draw two representative curves, right? So like, let's say there's R1, made up curve, right? Now let's say R2 is like this. What's happening is they intersect at 0, 0, 0. And you've got two tangent vectors here. You have a vector this way that's parallel to R1, and you've got a vector this way that's parallel to R2, and we want this angle between them. Well, that's pretty straightforward. All you've got to do is step one, find the derivatives, because the derivatives will be the direction that the curve is going at that particular point. So find find derivatives at, not just anywhere, evaluated at 0, 0, 0, because that's where we're doing this. They intersect at the origin. So R1 prime is, we just take the derivative with respect to t. So we have 1, 2t, 20t to the fourth, right? I'm just taking the derivative of t, t squared, and 4t to the fifth. Specifically evaluated at 0, 0, 0, we have 1, 0, 0. So that's the direction it's going. Do the same thing for the other one. R2 prime is, what do we have? -2 cosine -2t, and then -5 cosine -5t, and then 1. And specifically evaluated at 0, 0, 0, we're going to get, well, cosine 0 is 1, so we get -2. Cosine 0 is 1, so we get -5, and then 1. Okay, so at this point, we've got two directions. Okay, and we want the angle between them. So now find the angle between the two directions that we found. And I don't know if it's going to happen, but when they say acute angle, you have to deal with the fact that when you've got two vectors that cross like this, when you find the angle, you might find this angle. But if you find that angle, you just want to throw that out and take that angle, which you would do by 180 minus your answer. So if theta is greater than 90, use 180 minus theta as your answer instead. Okay, so let's go through this process. So what's the angle between vectors, right? So you look that up. What is the angle between vectors? I don't know why I'm typing that. I don't think you can see what I'm seeing anyway. So that's just wasted time. I should have just told you. Sorry. But what it is this, right? So you can say that theta is cosine inverse of, and in general, like u dot v over magnitude u magnitude v. So this is what we have to do for these two vectors. So if we do that, we have cosine inverse u dot v. I'm just going to mentally do this because it's easy enough. So we're doing the dot product between these two. I said u dot v, but it's going to be the two highlighted vectors. So 1 times -2 is -2. And then 0 times 5 is 0. And then 0 times 1 is 0. And I don't know why there's a comma there, but it should have been like plus 0 plus 0. All right, so there's the dot product. Then magnitude u magnitude v, actually the magnitude of these vectors. So square root 1 squared plus 0 squared plus 0 squared for the first one. And then 2 squared plus 5 squared plus 1 squared for the second one. So we've got cosine inverse of -2 on top. And then on bottom, 1 times radical, what's under here? 4 and 25 is 29 plus 1, root 30. So we need cosine inverse of -2 over root 30. And how are we going to type our answer in radians, maybe? Oh, no, they want degrees. So -2 over root 30. So I'm going to go back to my web browser. And how would we do this? So let's go back to my web browser. Where's my web browser? Give me my web browser. Okay. So the way you would do this is typically you need a calculator. And we'll go arc cos. That's the easiest way for me to type it in. -2 over square root 30. And I'm going to try to say in degrees, but I don't know if it'll know that. Understand that. And also, I typed it in wrong, right? Because that should have been 30. Oh, it's annoying. So let's go back here. So we do that, we get the answer. Oh, and there it is in degrees. So we have 1.4. Is that enough? Is that going to be enough precision? Doesn't say. But maybe I'll click on that and I'll say radians in. I just want more decimal points. I don't know how many we need. So 114 there. And we should be able to subtract, actually, because remember, this is the wrong answer because it's over 90. So we actually need 180 minus this. And we get, are you kidding me? Give me, why are you doing this? Right, like 68. Like, why are you giving me in arc minutes and stuff? Why can't you just give me it in? Oh, you know what? Nah. I just want the number. All right, so 68.58 whatever degrees. Also, I probably could have done this. I probably could have just said angle between my vectors, which were one of them was -2, -5, 1. And my other one was it 1, 0, 0, 1, 0, 0. And, if it came up with the exact same answer. Okay. Again, you still would have had to know to subtract 180. So coming back here, this should be, actually, let's just click on it and see how many decimal points it wanted. I was just going to put in 68.58. 68.58. I'm just going to do that. Is 2 decimals enough? Yeah, 2 decimals was enough. So yeah, all right. This one's exactly the same. Find the positive t value when this is perpendicular to this. That's straightforward. There's not anything to it. Just trying to, sorry. There we go. There's not anything to that. You just have to, take the dot product and set it equal to 0. Maybe we'll do that, and that'll be the last thing we do. Maybe. Yeah, that'll be the last thing we do. All right, so let me write down that R of t is 4t, 8t squared, 5t squared minus 5. All right, and we want the t value where r and r prime are perpendicular. So close that. Let's do this. So first you find r prime, which is just the derivative. So 4 and then 16t and then 10t. And then we want them to be perpendicular. The question is, what is t when, or for r is perpendicular to r prime? So perpendicular, you're going to do the dot product and make it 0. So that means that r dot r prime equals 0. That's what you need. So you just do that dot product. So r is 4t, 8t squared, 5t squared minus 5. Dot product with the other one, 4, 16t, 10t, and we want that to be 0. Do that dot product, you get 16t plus 8 times 16, 848. Is that 128? I think it's 128. T cubed, and then the last one will be plus 10t times 5t squared is 50t cubed, and then 10t times 5 is 50t equals 0. So you get this. You're gonna have to do a little bit of work here. So we have like 178 t cubed, and then we got negative 50t and positive 16t, so that's like negative, it's at negative 34t, something like that. Give me a second here. I don't know if I feel like I'm making a mistake because I feel like I'm just rushing here. But so we have this. If you were going to try to solve this by hand, the way you would solve it by hand is you would factor out a t and have 178 t squared minus 34 equals 0. Then one of your solutions would be t equals 0. And the other one would be when 178t squared minus 34 equals 0, which you have to solve. So you get t squared is going to be 34 over 178, and then t is going to be plus or minus square root of 34 over 178. They want a decimal there, so we punch that into a calculator. Low battery, please replace, no. Square root, you can't see, but 34 over 178 is 0.43 something. So this is t equals plus or minus 0.437, and it goes on. Hopefully you weren't just, okay, yeah, you were looking at this. So yeah, so like literally you just do what it says. It says, where is r perpendicular to r prime? Well, you make them perpendicular by setting the dot product equal to 0, and it only happens in certain places. A positive one, right? A positive, a negative, and a 0 in this case. And so they just, in particular, they have asked for what is the positive t value where this happens. And so you're just typing in 0.437. That was the positive one. All right, so I think, so we have unit tangent. Well, unit tangent, you know how to make a unit vector. You divide something by its magnitude. You know how to integrate things. And yeah, so that's going to be it for now. This went on longer than I needed. So I'm going to get this uploaded for you, and hopefully it's useful.